Yeah, a very quick video on algorithm complexity. So algorithm complexity is a kind of a measure of how long an algorithm will take to run relative to how much data it's getting. The more complex an algorithm, the less efficient it is. The idea is to keep algorithm complexity at a minimum where possible. So just look at quadratic complexity. So here's kind of a sentence that I've written about quadratic complexity. So it's an algorithm with quadratic complexity applied to data which has size n, for example, n nodes in a network, or perhaps n pieces of data to be sorted, or something like that, which takes t computations, or t amount of time, to complete, will take approximately k squared times longer, or have k squared times more computations for a data which has a size kn. And we notate this as O(n) squared. It's called big O notation, and it just means that the algorithm has an order of n squared. So not a great sentence for an example, so I thought this might help clear things up a little bit. So this is just for quadratic complexity. Let's say we have 10 nodes on the network and we're applying an algorithm with quadratic complexity to this network, and it takes t time. Might be a minute, don't know, might be an hour. If we double the number of nodes, so we've times it by 2, then we times the time by 2 squared, because it's quadratic complexity, so it's 4 times longer, approximately. If we times it by 5, then it's going to be approximately 5 squared times longer, so it's going to take approximately 25 times as long. Times it by 10, it's going to be 10 squared times as long. Times it by 1,000, it's going to be approximately 1,000 squared times as long to compute, or 1,000 squared times more computations. We can extend this then above quadratic, and we can extend it to cubic complexity as well. Exactly the same principle, except that this definition here would have k cubed times more computations. So an example of cubic. Again, we've got the same numbers down the side here, but this time with cubic complexity, it's going to be times that kind of scale factor cubed. So to get from 10 to 20, it's times by 2. So that's going to be times 2 cubed. To get from 10 to 50 is times 5. So that's going to be 5 cubed. And we can see by the time we get to 10,000 nodes on a network with a cubic complexity algorithm, it's going to take 1 billion times as long, because that is 1,000 cubed. You can have other complexities as well. So you can get logarithmic, exponential, linear. There are other polynomial ones, so quartic, quintic, and so on. And some of the algorithms, you need to know what complexity they are. So prims and Kruskalls, you need to know that they are both cubic, and Dijkstra's, you need to know that that's quadratic. Sorting algorithms tend to be quadratic, so bubble, shuttle, selection, and interchange are all quadratic complexity. This is more accurate if n is really big. Because if n is big, then the linear term here and the constant term, they tend to filter out, disappear, because they're less significant to the quadratic. So the bigger n is, the more accurate this is.